of Metropolitan Talks in Math and Physics. So today we have our speaker, Mr. Reaz Shafqat. So he did his MSc in theoretical physics from the University of Dhaka, and now he's acting as a teaching assistant at BRAC University. He's going to talk about integrability from oscillators to nonlinear Schrodinger. So let's welcome the speaker and have a round of applause.
Okay, so am I audible? Yeah, okay. So hello, welcome everyone. I'm Reaz, and today I'm going to talk about integrability from harmonic oscillators to nonlinear Schrodinger equation. So before I start, I want to give a quick disclaimer. That is, from Hardy's mathematician's apology, I'm going to give a physicist apology. So that, why do I mean by that? Okay. So why do I mean by that is today I can see a lot of mathematicians in the audience. But today's talk is mostly about differential geometry. But since due to time constraint, I won't be that much mathematically rigor, and so I might offend you guys. So be patient. Okay. So that is why my apology. Okay. So let me show you a quick outline of today's talk. So today we are going to talk about some smooth manifolds, mainly Poisson manifold and symplectic manifolds. Then we are going to derive the Liouville integrability theorem and illustrate the harmonic oscillator example. Then afterwards we will go through the Liouville-Arnold theorem and finally talk about. Is this like oh yeah. Then finally, we are going to talk about the limitations of the Liouville-Arnold theorem, and we look at the Lax operator construction, which is currently a modern way of doing integrability of classical systems, also as well as quantum systems as well. Next, we look at the R matrix and the associated Young-Baxter equation. So anyone who has attended the talks of Nafis Bhai surely knows what these things are. So, and they also know what does the role of R matrix and Young-Baxter equation in integrable theory. So be sure, if you haven't checked his videos, please check his video lectures. And finally, we are going to construct the Lax operator field theory version and the nonlinear Schrodinger equation. So apparently for today, I'm not going to go into rigorously into the nonlinear Schrodinger equation part, since it is a mathematically heavy and we don't have that much time for that, since all of the topics take each lecture. So we have to do a lot of rushing today. So, but for today, I will only restrict myself into only classical systems, not quantum. Okay, so no quantum today, only classical. Okay. So first of all, what do we mean by integrability? So when we study integrability, it is actually a blend of two fields, the algebraic geometry and representation theory. But however, in the literature, there is no exact definition of integrability. There are some glimpses of definitions like we need conserved quantities, we need many conserved quantities. The more, the better. Okay, so actually we will go through some definitions today. So from approach to approach, the definitions changes, but the overall idea is same. We need conserved quantities. So first of all, when we do some mathematics and when we do some physics, we need some playing ground. And for integrability, we have a playing ground, the background, that is the smooth manifolds. So for smooth manifold, what do we mean by that? It is a topological manifold with C infinity compatible charts. I mean, if I don't say it is Hausdorff second countable, mathematicians will be offended today. So I'm saying that it is Hausdorff second countable and locally homeomorphic to Rn. And so pictorially, so our manifold looks something like this. So we have a manifold, we have open sets, U and V, and we have C infinity maps to the Rn's. And we also have the chart compatibility maps as well. Okay. So examples of smooth manifold, we all know what smooth manifolds are. Maybe I can write some. Rn. Next I can write is Tn, torus, also sphere, Sn, many more. So these are the commonly known smooth manifolds. So when we go a bit further, we have the tangent space. So what are the tangent space? So at every point in the manifold, we attach a vector space of constructing of the tangents to that constructing of the tangents, and we construct a vector space based on using those tangents. This is achieved by taking the directional derivatives of equivalent classes of curves passing through the points. I think anyone who has introductory differential geometry knows the germs of function and other stuff as well. So we take tangents, we define tangent space by using the germs of function and afterwards. So pictorially, tangent space, vector space looks something like that. We have a manifold, and on a point we define a vector field, and this is a tangent. This is our tangent, and tangent space has some properties like tangent space. It has the same dimensions as the manifold, and also in local coordinates we have some basis for our tangent spaces as well. The next thing is the cotangent space. I think it is algebraic. I should be careful. It is the dual of the tangent space, and also it is convenient to express the tangent space using one form. So what is a one form? So it is when we have a smooth map from the manifold to the reals. One form can be derived using this exterior derivatives. And what does the one form do? One form takes in an element from the tangent vector space, and then it spits out a real number, like from the definition we are seeing here. Okay, so some properties, quick properties is cotangent space is also a n-dimensional manifold. It has the same dimension as the tangent space, and I think it is isomorphic as well, right? Yeah, it is isomorphic also. And the suitable basis for the tangent space can be written using differential forms, like the one forms in local frames. Next, now that we have defined some differential geometry, we are getting towards physics now. Okay, so for that we need to impose more stuff, and that is the Poisson bracket. So now we are going to impose Poisson bracket in our manifold. So a Poisson bracket should be something like, in our manifold we have a smooth manifold, and now we want to define what a Poisson bracket. So it is a quadratic map. So it takes in two functions from the manifold, and then it maps to a real, actually a continuous function. So we all know, anyone who has done classical mechanics also knows the properties of Poisson bracket. So we know it's skew symmetric. It has Jacobi identities, and it follows Leibniz rules. I think I forgot to write about the linearity property. I guess. Okay, so in local frame, Poisson bracket has a following form, which I think which can be expressed using a Poisson tensor. So Poisson tensor is basically a two-component contravariant tensor. And also it takes in two one forms and spits out the Poisson bracket results from the Poisson bracket as well. Okay, so next we do the real deal. That is where our usual classical mechanics happens, is the symplectic manifold. So when we define a symplectic manifold, we need a Hamiltonian and other stuff. So when we have a system which has a Hamiltonian, that means we have a symplectic manifold. Okay. So a symplectic manifold is also a smooth manifold of 2n dimensions. The dimension, this is very crucial. 2n, the number dimension has to be even. Okay. So, and also it has a two form. It has a differential two form, which is open and also non-degenerate. What do I mean by that? Which is closed and non-degenerate. By closeness, I mean it has the one form of its of the omega is 0 and non-degenerate. That means it takes in a map from the tangent vector space and spits out a cotangent vector. And this map is isomorphic. in a local coordinate, so the omega takes on the following form. We can use one forms to write the omegas. So for a typical example for the symplectic manifold is our Euclidean 2n dimensions, where the symplectic form takes on the P wedge Q, and we have a one form. The alpha is one form. Okay. Yeah. So basically, what two form does is two form takes in two tangent vectors and splits out a real. Okay.
Two vector fields.
Yeah.
Fields of the function.
Yeah. If we take vector fields, then yeah. But if we take a tangent space on a point, then it splits out a real.
It's a two form ULC.
Okay. Okay. So next is the comparison between symplectic manifold and Poisson manifold. A symplectic manifold contains a Poisson bracket structure. How can it contain it? So our symplectic form is actually the inverse of the Poisson tensor. Okay. So by that, using that, we can redefine our Poisson bracket using the symplectic tensor. Using the symplectic form, and here we have reutilized. We have introduced a new thing that is this xi of f. That is the vector field generated by a scalar function. That is f. Okay, so this defines a flow in my manifold. However, the other way is not true. A Poisson manifold may not be symplectic. Can anyone say why? Does anyone know why a Poisson manifold may not be symplectic, but symplectic manifold always require a Poisson bracket structure? So actually, it comes from the idea that J is invertible or not. Okay, so if J is invertible, then the Poisson bracket boils down to the we can define symplectic manifolds from Poisson manifolds. If not, then we cannot define them. Okay. Next, we arrive at a crucial point, that is the Darboux theorem. So for every symplectic manifold near around a point in my manifold, there exists some local coordinates. Okay, so these local coordinates can be used to write down my symplectic form, which is of this type. And this symplectic form is locally symplectomorphic to our Euclidean 2n dimensions. So what do I mean by that? Symplectomorphic. That means that it is diffeomorphic, plus it also conserves the volume of the phase space. Also, this theorem enables canonical transformation. Like in every classical mechanics problem, we use canonical transformation. So this theorem allows us to do canonical transformation, as we can see canonical transformation in the diagram between two flows in the phase space. Okay, so now that we have defined our background playground, now let's see some actions. So by action I mean the Hamiltonian. Okay, so my Hamiltonian is also a function of the phase space, and we define a flow using the Hamiltonian function with the interior product. And this flow describes time evolution of the system. Like say for any variable, this is xi of h takes in a function from the manifold, and then it spits out the Poisson bracket corresponding to that function. So any function of the phase space can have the following form, can be written like, I can also write it in this way. Yeah. And pictorially, I have my funky looking manifold where the arrows denotes the flow in my phase space. But we know that we have conservation laws as well. So in that cases, we have we get the Poisson bracket with the Hamiltonian at 0. So pictorially, what does it look like? So it looks so that means that the flow is along the level sets of the function in the manifold. Okay, so now we are going to have our first definition of integrability. So our first definition is the Liouville integrability. So Liouville integrability it gives us the first complete definition. That is, for a 2n dimensional symplectic manifold, we have our system is completely integrable if there exists n smooth functions, f1 to fn, and one of them has to be the Hamiltonian with the following properties. They have to be linearly independent. That means their one form is the linear combination of their one form does not give me 0 unless the coefficients are 0. Then they have to Poisson commute. There's a cool name for that as well. That is the involution. I think it's also given in the literature of the differential geometry as well. So this theorem allows us to solve the equations of motion by quadratures. So by quadratures, what do I mean? So quadrature means that we don't have to solve differential equation. We just have to do some substitutions, algebraic adaptations, and integrations. That's it. No solving differential equations. Okay. Now, next comes the modification of the Liouville integrability theorem. That is a Liouville-Arnold theorem, where we have the same construction as before. We have the n smooth functions like before, and one of them also has to be the Hamiltonian, and they also mutually have to be involute. That means they have to Poisson commute. Next is they have to be functionally independent, and besides that, we need furthermore criteria that our motion is restricted in common level sets in the manifold. So, and the level sets are compact and connected. So in that cases, so the connected component of my manifold is diffeomorphic to a torus, okay, n-dimensional torus, and my motion is confined in a Rn cross Tn dimensional manifold, and there exists local canonical coordinates such as the action angle variables. So this theorem allows me to construct action angle variables that we have seen in the classical mechanics. Okay, so which have the following two form, and my Hamiltonian simply boils down to just functions of the actions, not the angle variables. Okay, so let's see some of the properties of the action angle variable. So the action angle variable is defined as the integral over a closed loop in my manifold. So this is my action, definition of my action. And the variable, my angle variable, okay, there's a typo here, it should be angle. Okay, so the angle is parametrized over the circle, and it is a modulo 2 pi capturing the periodicity of the manifold. So pictorially, for the action angle principle, the dynamics takes on the tori that I mentioned in the previous slide, like Tn tori. So pictorially, there is a cool way in differential geometry literature, like the dynamics creates I think the dynamics is associated with the symplectic leaves in the manifold. So my motion is confined, like as you can see from the arrow, like confined on the torus, and my equations of motion simplifies to this, where my action is time independent and my angles are linear in time. Okay, now we come to our favorite example, that is the harmonic oscillator example. So a typical Hamiltonian for the harmonic oscillator is similar to this. So we all know the Hamiltonian. So yes.
Yeah, this one. So in this slide, you've written that the manifold is Rn times Tn, right? So there is this tag in the theory of Lie group that every connected abelian Lie group is isomorphic. Some integral space and is product with some form. So is that is there a connection between that?
Can you state the theorem again?
Every connected abelian Lie group is isomorphic. Some Rn times some T to the n.
It could be, I think. Yeah, it could be. Okay, so pictorially, the harmonic oscillator problems look something like this. I've used the spring system for my illustration, and the equations of motion look something like this, and the corresponding two form for the harmonic oscillator. But we know that for this system, we have energy conservation, and my phase space has a dimension of 2, and we have one conserved quantities. So this clicks up well, like we can use Liouville's theorem here. So for the harmonic oscillator problem, we have the phase space is of dimension 2, and we have one conserved quantities, so we can solve it by quadratures rather than solving the differential equations. Okay. Okay, so now I'm going to solve it. So for the harmonic oscillator, let us write the p square plus omega square q square. I've taken the mass to be 1, because why not? And we have our conserved quantities, that is the energy. So half of p square by omega square q square, and which gives us, let's express 2e minus omega square q square.
What is the manifold? R2.
Manifold is the ellipse. Yeah, manifold is the ellipse for these cases. Okay, and next is we define the action. Next. And if we solve this integral, I'm just not going to go through the detailed process. I'm just writing the integral because I should write something. Why not? Let's not present everything on the slide. It's since it's a mathematics and physics talk. So if I solve this equation, I have something like E by omega. So as we can see, this is constant. And this is what it's supposed to be. Like for our theorem, Liouville theorem, we have the Liouville-Arnold theorem, we have our action to be time independent. So since this is constant, energy omega both are constant. So we can see that it is this is consistent. Next, we define the generating function. So the generating function looks yeah, it should be with the I d of 2I omega minus omega q square. And we know that our theta is something like di. So we have omega dq 2I omega minus omega square q square, and which gives me actually the arctangent omega q I omega minus omega square q square, and ultimately this gives me, we can finally doing some, I have to, sorry about that. There is an issue with PowerPoint. So as I was writing, so 2I omega sine of theta and so on. And also we can also further show that our dq is also equal to this. Okay, so our
Here, what the manifold is. You were saying that it's the ellipse,
yeah.
one dimension.
So my motion is confined in the ellipse. So actually, this is like locally this we have. It is diffeomorphic to Rn, right? So R2, but the motion is confined in the ellipse, right? So
Is it tangent bundle of the ellipse? It is one dimension ellipse.
Yeah, this right. So my motion is confined in this.
That's the configuration space.
No, this is my phase space.
The phase space is the dimension.
Yeah.
I think what he's trying to say is that the phase space is R and the motion is
Yeah.
the configuration space.
But it appears to me that it's not R2. Yeah. Something like cylinder.
Okay.
So the tangent space is around.
Shall I carry?
Yeah.
Okay. So now that we have solved the equations, like the symplectic forms as well. So now we look at some of the limitations of the previous theorem, that is the Liouville-Arnold integrability theorem. So we know we have to find a way, like we need a way to find the mutually commuting observables. Like for harmonic oscillator problem, we were lucky we knew the conserved quantities. So that is my energy. But for in a generalized case, we don't know. So we need a way to find them because they help us in solving the equations. Also, what about systems that are partially integrable? Like, say, for example, in the Liouville-Arnold theorem or the Liouville theorem, we had something like if our phase space is of dimension 2n, then we need n integrable, n conserved quantities. So what about if we have n minus 1 or n minus 2 conserved quantities? What about the integrability of those systems? How can we define integrability in those cases? And also, what about the, yeah. Yeah.
So when you say you are talking about partially systems that exhibit some
the integrability usually focuses on, say, systems that can be directly solved. So in integrability, we don't usually consider perturbation theory.
let's say for a generic electric potential, right?
Okay.
Like a nonlinear potential. Let's say that has a potential which is a function of x.
Yeah.
So when you're talking about partially for that system, if you work in low energy, the region of low energy,
I get it.
low energy, that would be, but once you break a certain threshold, whole thing becomes there.
Yeah.
Do you mean this type of system, you say, partially?
I'm by that I meant a generalized. Yeah, your one could be an example for that case as well. Like maybe when you have systems like the one you're mentioning in low energy scales, we don't have we don't have chaos. Maybe for high.
Yeah, because in low energy you are working out.
Yeah.
Everything is integrable.
Yeah. So, like in higher energies, we may not may not have that luxury. So, in those cases, what can we do? So, and also, what about we mentioned like we have connected and compact compact levels. In those cases, what if we don't have those luxuries as well? So, for those problems, we turn down to another representation called the lax representation. Actually, this representation doesn't solve all the problems. It solves some of the problems. Okay. So, lax representation actually converts a nonlinear problem to a linear problem. Okay. So, what do I mean by that? I'm going to show you. Okay. And it also enables a way to calculate the conserved quantities as well. I will also show that how to do that with lax operators. Okay, and this method uses the luxury from the spectral methods like the eigenvalue problems and so on. So for this method construction, we need two square matrices of the size of the phase space. Like say we have the L and the M. They are one is the lax operator, lax matrix, another is the auxiliary matrix, and the entries of the matrix has to be some functions of the phase space. Like say it could be position momentum or something like that, energy. It could be some function we don't usually, that are not of physical interest as well. And also the system follows the following equation. This is called the lax equations of motion. Okay, so for here we have the commutator. So lax operator, what does this method is provides an alternative to the Liouville-Arnold theorem that we have seen, and also this method reformulates the dynamics in a linearized way, and this is mainly an algebraic.
When you wrote that equation,
yeah,
your L depends on T. T is the parameter, right?
Yeah.
So one parameter family of what?
One parameter?
Depends. So L and M are supposed to be matrices.
Yes.
With entries being functions on the phase, right?
Yes.
But now it seems that they also depend on T.
I see. I should have omitted this part because since I'm
that's okay. It can depend on T, but you have to define one parameter family or something.
No, it actually, we are going to see that the lax matrix ultimately boils down to they're basically isospectral. So ultimately, we are going to see that the eigenvalues are not changing. So
when you write L down, what do you mean by?
So this is actually a way of mimicking the Hamilton's equation. Actually, this is a more compact. This is a compact way of writing the Hamilton's equation. Nothing else.
So you are not taking one parameter family.
No. This is actually a compact way of writing the Hamilton's equation. Okay. So, but the downfall of this method is we have to find what are the L and what are the M's. Okay. So, but as I mentioned, like this approach gives me a way to calculate the conserved quantities. So the conserved quantities can be calculated by taking some powers of the lax matrix and tracing it up. So, and this K can be some integers. Okay. So next thing is, how do we know that they are conserved quantities? So we just take the time derivative and using the properties of trace, we can show that they don't vary with time. But there's an issue. Yeah. M is an auxiliary matrix. Auxiliary matrix associated to the system. So for this construction, we need two things, the lax matrix. So L and M together are known as the lax pairs. So for a system, we need both. We just can't define one. Okay. So here is an issue, right? So we know like K's are integers. So and integers vary from -infinity to +infinity. Then does this mean my system has infinitely many conserved quantities from this lax construction? Like I can take any power of the lax matrix and then trace it out, and then I might get a conserved quantity with my formula.
But not only
Yeah.
infinitely different, M and L to the M may have the same.
Yeah, exactly. That is what the thing is. Yeah, they may not. They may be. There could we have found a way to calculate infinitely many conserved quantities, but they are not functionally independent. By that I mean they're one forms. So they may not be linearly independent. The one forms may not be linearly independent. Okay, so now we have our equations of motion, and with a given initial condition, like every dynamics problem we do, we use an initial value problem and then we solve it. So for this matrix equation that we have here, the lax equation, so we can also solve this equation using some invertible matrices. And for that cases, my auxiliary matrix takes on the following form. Okay, so next is we know that we have infinitely many conserved quantities. So, and from Newton's formula, we can we know that the conserved quantities are also the eigenvalues from L, because we have defined them by taking the traces of powers. So that means the eigenvalues of L and I's are some connected. So this means that since my conserved quantities are time independent, that means L has to be isospectral as well. That means it doesn't vary with time. So if we can somehow diagonalize my L matrix, then we may have just solved the problem of the dynamic equations. Okay. Now we turn again to our harmonic oscillator problem. This will be our favorite problem for today. And for this case, again, we need for lax construction, we need the L and the M matrices. Luckily, the L and the M matrices are known. Okay, so we can easily solve that problem. So for the lax representation, the L takes on the following form: P omega Q minus P, and the auxiliary matrix. So I have written the form of lax matrix and the corresponding auxiliary matrix, but how do I know this is the case? So actually, we have independence here. So there are actually ways of finding them out, but we won't be visiting those techniques here. But I have written them considering the Hamiltonian is. And my equations of motion are so keeping them in mind, I have written the lax operator and the corresponding operator. So if we now plug into the formula, we can show that they actually give me this equations of motion. So keeping the equations of motion in mind, I have taken a suitable lax form. I could have taken any lax form, but one thing I must satisfy is that this should represent the lax equation should reproduce the equations of motion. Okay, so now is how do we solve this with the lax matrix? So in a prior slide, I used a definition for the M. So I can use this and then right multiply with G in both sides. And then this gives me an exponential of that. And then finally, using my initial condition, I just simply can solve my equation. That's it. So for the harmonic oscillator problem, we started with a suitable lax pairs and then we did solve the equation. But we have a freedom in that. We have a freedom like we can take another lax pair and we can multiply. We can left and right multiply like we have with some invertible matrices. That also depends on the dynamic variables, and we can show that this M prime and L prime also represents the dynamics of the same system, but in a different representation and nothing else. So here is the tedious algebra behind it. So we can see that this takes on the this actually is the new auxiliary matrix, and this is actually the new lax matrix. So actually we have a freedom here. So the lax matrix I chose prior are not actually the lax matrix we always want to use. We can use different lax matrices as well. So, but the difference, we have a freedom based on this invertible matrices. Okay, so we can also see that M has something called a gauge transformation. So I'm not going to talk about gauge transformations and other stuff today. And lax matrix, so we have defined lax matrix using commutators, but we don't know the Poisson bracket structure here as well. Currently. So since we are doing classical mechanics, we need Poisson bracket structure. So for the Poisson bracket structure, and we also don't know how the conserved quantities, are the conserved quantities involute or not? Like do they Poisson commute or not? So we have to establish that as well. So this can be established by using the Babylon and Wallet theorem, and this states that the eigenvalues of my lax matrix is equivalent of finding that there's a matrix called R matrix, and R matrix has a special significance in integrable theory. So again, I'm stating if anyone who has attended Nafis Bhai's lecture knows what R matrices are. And he also stated time and time again, like the significance of R matrices in integrable theory. So as I'm stating, like the involute properties of my conserved quantities actually boils down to spatial matrices between two n-dimensional matrices. Okay, so we can define the lax operator. So taking actually the Poisson bracket of the two lax operator is equivalent of taking the commutator of the R matrices with two lax representations. By two representations, I meant like taking the lax operator and tensoring it with an identity, or tensoring it with an identity and taking it the lax operator. And finally, if we write the equation in an indices form, we arrive at our next equation. And so basically the eigenvalues of this, the L's, the lax operators are, so if they commute or not, that actually is encoded in these R matrices. Yeah. One is commutation and one is Poisson bracket, yes. So but for that, to show that we take that L to be diagonalizable. So we take a similarity transform for our lax matrix, and next is we plug into our Poisson brackets, and then we know that they have to Poisson commute because we want them to Poisson commute. And then after some tedious algebra, and we did some substitutions as well, which finally gives me a form. So now we compare this equation and the the equivalence relation, and we see that R can be expressed as the following way, and this is the famous R matrix in integrable theory. Okay, so for our harmonic oscillator problem, we have the R matrix can be defined in this way. But here's a catch. This R matrix is also not unique. Since our lax representation was not unique, so the R matrix will also not be unique. Okay. And finally, if we take like tensor products of three spaces, yes. E's are identity matrices. It's basis for the matrix.
1, 2 would be the
row 1, column 2, 1, and rest of them are.
diagonal. We want to be 0.
All of the entries are 0 except for one in row 1 and column 2. Yeah. So afterwards, if we use the Jacobi identity, and we use our equivalence relation, and then we can see that we arrive at. We are just substituting here, nothing else. And if R is independent of the dynamic variables, that means that the Poisson brackets in the prior slides. So this stuff becomes 0 because in the Poisson bracket there's a derivative, and so if they are independent, that means those derivatives give me 0. So this gives me 0. So ultimately, what do we have here? We have an equation. This is known as the famous Young-Baxter relation. Okay, so this is done for the classical system. So Young-Baxter relation pictorially looks something like this. So for this, so let us take this one to be phase space 1, phase space 2, phase space 3. 1, 2, 3. So this one is R12, this one is R13, and this one is R23, R23, R12, and that is, no, this is actually R13 and this is R12. So this Young-Baxter relation has some following importance. Like this Young-Baxter relation decomposes my integrable theory. Like when we have three particles scattering together, this Young-Baxter relation decomposes into like two body scatterings. So when we have three bodies going into one point, we can simply, this is equivalent of writing two body, 1 and 2, then 2 and 3, and 1 and 3, or the other way around. Yeah.
So you're saying this Young-Baxter relation number the three bodies scattering. But what happens is this is where we plus is this equivalent or is there anything else?
No, they're not equivalent. No. So this is actually like we don't lose the scattering information. So from this relation, I know that we don't lose the information after each scattering. Like when we are scattering, and afterwards, like say after many times, like say we are showing it for three body, like we could have 4, 5, 10, and for each three body interaction, four body interaction, like I can utilize another as well. I can use another as well for each.
When you are talking about losing information, there's a whatever measure, classical scattering angle, or how much energy is there?
I think by losing information, I'm stating like the system doesn't fall into the chaotic regime, rather than it falls into the integrable regime. Okay. So also the Young-Baxter relation means that my theory is integrable. Okay. Okay. Next is we introduce another parameter for our lax representation. That is a spectral parameter. So we can modify our equations of motion with an additional parameter that is a complex in nature. And for that case, we also modify our conserved quantities as well. So for these equations hold for any lambda. Okay, for any complex number lambda. So this gives me another degree of freedom. Like we can tune the parameters of the system. Like we have a control parameter, we can tune those as well. So there are some uses in the classical mechanics as well, like say the Kepler problem, the Neumann problem, and other many more. But for our harmonic oscillator problem, we don't actually need them. So I'm not going to explore them. But there is a cool way of writing the conserved quantities, like we take the LoRa expansion around the poles of the lambdas, and then we can write the conserved quantities and other stuff like observables. Okay, now we come down to the final topic of the day, that is the nonlinear Schrodinger equation. Okay, so this is a very mathematically heavy thing, but I won't discuss so much mathematics here because this actually takes a lot of PDEs and other stuff. So for this nonlinear Schrodinger equation, we know that our variable, the dependent variable, is a complex valued function with real x and time greater in the positive half space. So nonlinear Schrodinger equation has applications in many fields, like in nonlinear optics, plasma physics, and many more. So the goal is to represent that equation with the Lax pair equation and maybe solve the equations as well. So for converting that equation into the Lax pair, we will look at Zakharov and Shabat's construction. That is, we take the nonlinear equation. So for initial time, we know that we have some initial value of my problem. So we take the asymptotic values, like say for x equal to plus and minus infinity, the solution has to go to 0. Or we can take any other boundary condition. For different boundary conditions, the Lax pairs vary. So for my case, like I've taken the 0 boundary condition at the infinity. And then we introduce a column vector. Okay, this is not actually the wave function. This is actually a column vector. And they are also the functions of space and time. Okay. This construction actually allows me to write the nonlinear equation into two couple sets of linear ODEs. So this construction allows me, so by this means derivative with respect to x, and this is partial derivative with respect to time. So this gives me a coupled linear equation. So, but did we lose any information or did we lose anything else? Like how do we know this construction works? So we just have to take u and v of this form. So next is, why are we taking this form? So it turns out, like if we partial it with u and if we partial it with x, this is actually like taking u of x and t and u of t and x. So we know that derivatives commute. So these two has to be equal. So this two has to be equal. And for that cases, we do some similar adaptations here. And we can show that this is actually the representing this equation. Yes.
Just one is, are you restricting yourself to one dimension?
Yes.
And
integrable theory currently
because if you if you go over the rhythm, you get collapse. Right?
Yes.
Especially if you have the
yes.
And I think you are working for the focusing piece.
Yes. Yes. Yeah.
So all of like you want to be integrable, all of one dimension.
Yes. For integrability, actually, this is an open problem, like how to define integrability in more than one spatial dimensions. I think they are actually defined for 1+1 dimensions currently. One time and one space. Yeah. We don't know how to define integrability. Like, say, we have integrable models for one-dimensional Heisenberg spin chain, but we don't have two-dimensional Heisenberg spin chain.
Yeah.
Yeah. Okay. So this equation is also known as a zero curvature condition. Yeah. Yeah. Yes.
And is that only for putting it on?
Yes. Yes. Yes.
Seems like the that you have
Yes. Yes. They are actually gauge connections. Yes.
like the time component of the gauge field and
Yes. Yes. Exactly. Actually, this thing is actually the time evolution of this column vector that I've written. And for this zero curvature condition is also known as the compatibility condition. Like if this,
could you compute the connection of this, curvature of this connection that's going to be zero?
yes, yes. That means like if we take a parallel transform, it doesn't matter which path we take.
That connection.
Yeah, this is the flat connection. This is also known as the compatibility condition for integrable theory. Like any integrable field theory has to be compatible, has to follow the compatible condition. So now we will solve the nonlinear Schrodinger equation. So first we have the initial condition. Okay, so we are going to plot it to scattering data. Okay. So at time t equal to 0, we know like at infinity, our solutions become 0. Okay, so we are solving our equations at x tends to plus minus infinity. Okay. So using the first equations, I think. So if you look at it, the coefficients, the off-diagonal coefficients are u. Since we are taking them to be 0, like say we are taking, since our wave functions is dying out at the infinity, so they are zeros. So ultimately, this equation boils down to solve. This is actually a very easy equation to solve. This is actually known as the Jost solution. Some guy named Jost solved it. So asymptotically, my wave function can be represented wave. I'm not supposed to say that as wave function. Okay. So asymptotically, the two component function is represented as the column vectors, like waveforms. So next case is we take the linear combination of the two asymptotic forms. Okay, for x equal to x going to positive infinity and for x going to negative infinity. Okay, so as we can see that the coefficients are kind of like similar, like b star, because if we look at the previous, why isn't it showing? Oh, there's a delay here. So like if we take the positive, we are taking linear combinations of these two, and if we if we take the conjugate of one of them, we arrive at the other one. That is why. So if we take the solution at positive infinity, we take the conjugate, we arrive at the solution at the negative infinity. So that is why we are using linear combination and writing it in the compact expression. So depending on lambda, we have two types of solutions. So one is the discrete and the bound states. So for that cases, we demand that lambdas to be complex numbers. For bound states, we have soliton solutions. And for those cases, we only take pure imaginary lambdas. And the etas are determined using a method called the shooting method, and I'm not going to describe the shooting method because they require tedious amount of mathematics, and we don't have that time here. And also there's one another thing is that the eigenvalues for the discrete case is norming constant. That means like it doesn't evolve with time. Okay, so it is fixed. And we have another case that is the continuous case. In that case, our spectral parameter, that is the lambda, that is real. And for that case, we can define the scattering matrix. And from the scattering matrix, we can define different types of coefficients, like transmission coefficients and the reflection coefficients. Okay, so now we time evolve the scattering data. So for reflection data, we will time evolve using unitaries, and for the discrete cases, they are just same because they don't time evolve, because the eigenvalue for the solitonic cases is time invariant. Okay, so this is achieved by taking the second auxiliary equation, the one that is relating with time. Okay, so here also we have taken the asymptotic case. Like if we go a few slides back. Like here. So we set this stuff to be 0 as well, the asymptotic case. Okay. So, and for the final step, we will recover from the time evolved scattering data. We are going to recover the u, our dependent variable, the thing we are trying to solve in our nonlinear equation, Schrodinger equation. That is this u. Okay, so we do that by taking a Gelfand-Marchenko integral equation that have the following form. So, yes, you have a question. Okay. Okay, so this integral equation, I'm not going to show how to solve this integral equation. Maybe on free time, we will toil with this integral equation. But for the time being, we are just going to see what the terms mean. So the K means the integral kernel, and the F is actually contains the scattering data. So for this, we can see that it contains the scattering data for the reflection coefficient. And for this, we can see the discretized cases. Okay. But for this problem, we are mainly interested in the discretized problem. So we are just going to omit the continuum part, the reflection part. Okay. And so we solve the integral equation. And in order to determine our variable, u, so we just take the derivative. And this gives us the solitonic solutions for the nonlinear Schrodinger equation. So we have constructed, using the inverse scattering method, we have solved the nonlinear Schrodinger equation, the solitonic cases, the bound states, actually. So that is all it for today.